Good morning. We are going to continue studying the component importance. 창원에 없나?
네.
The first naturally occurring measure is the Bohm measure. It's a partial derivative of the total system reliability with respect to their component reliability. Important conclusion of Bohm measure is that the Bohm measure of component I is independent of the reliability of the component itself. Assume that we are working in a systematic society. The Bohm measure tells us that if we wanted to improve our contribution to the society, we should improve the reliability of others, not mine. So it is useless to improve your reliability in order to increase your contribution to the society. Believe or not, that's the implication of a Bohm measure. Okay, so it seems, even though it is actually correct, it seems that the Bohm measure is a little embarrassing, or looks unreasonable. So we introduce other measures. I added this figure. H is the system reliability. HPT is the current system reliability. H0I PT is the system reliability, assuming that the reliability of component I should be 0. Okay? The lowest level is, of course, the system reliability is 0 when all the component has 0 reliability. So this is the bottom. Okay? The system reliability, assuming that the reliability of all component is 0. Because the reliability of all the components is 0, the system reliability should be 0. The maximum value of system reliability is, of course, 1. This can be achieved if and only if the reliability of all the components is 1. This is kind of imaginary system. No system can have the reliability of 1 at any time. The reliability should decrease with time. This is another kind of imaginary ideal system. The reliability of component I is 1. So this reliability should be greater than the real system reliability, because the reliability of component I is equal to 1. This reliability should be less than the current system reliability, because the component I has 0 reliability. So this is kind of level of the system reliability depending on the component reliability. improvement potential is H1i pt minus hpt. Mathematically is confusing, but take a look at this figure. This is just difference between two reliability. This is the ideal reliability, assuming that component I has 1, has reliability of 1. Component I is perfect. So now you can understand why it is called improvement potential. This is the difference between these two reliability. The potential when the reliability, the current system is improved if the current system has a component I, which is perfect. In practice, it is not possible to have a perfect component. Any component, any system should kind of reliability that should be decreasing with time. So sometimes we introduce a parameter or kind of actually achievable reliability. So this is where PIN is the reliability of replaced component or improve that should have improved reliability. Any question? Good. Second is about risk achievement. What is risk? Risk is frequency times consequence. In this case, risk is regarded as the unreliability. Okay? Unreliability is just 1 minus reliability. Okay? This is the unreliability. And unreliability, remember that reliability is probability. Reliability is the number between 0 to 1. Okay? So reliability is probability that the system can fulfill its function at a given condition. So unreliability is kind of probability of failure. It's kind of definition of unreliability. So 1 minus HP, 1 minus HP is the unreliability over probability of failure. And 1 minus H0IPI, there should be a comma here. This is the numerator of the equation. So this achievement worth is the ratio of these two probability. That is current reliability divided over the unreliability of the system, which should not have the component, over the component has 0 reliability. So this is risk achievement worth. So if we combining the probability, we can generate many component importance measures. So only several component measures are selected for the application. This is the risk reduction worth. This is the unreliability of the system with perfect I component. So this is the unreliable. This is the 1 minus 1 IP. Is this okay? And this is the current, real, actual reliability of the current system. So it's the ratio of unreliability of a system with the actual component divided by the system with the component perfect I component. So it is measurable what? Reducing or removing the failure of a component I in achieving the current level of system reliability. Can you understand this meaning? Reducing or removing component I okay, that's enough. Actually, most important. So you'd better give a 10 or 20 minutes to understand the meaning of physical meaning of this equation. Anyway, Bomba measure and this measure, criticality importance, are the most important two component measures. First, Bomba. Second is the critical importance. ICL is critical importance measure. This is defined by this equation. So I add this part. This is a definition of Bomba measure. And this equation, this term, is exactly the same as this term. 1 minus p, partial derivative just means minus round p. 1 minus hpt is just partial derivative hp. What I mean is, Bomba measure is contribution of component I reliability with respect to the total system reliability. So we can, this is the reliability, we can replace the reliability with unreliability. The contribution of component I's unreliability to the system's unreliability. This is the two definitions are exactly the same in a mathematical sense and as well as in a practical sense. So 1 minus pi is the probability of the probability that the system is not functioning at time t, or the system get failed at time t. So it is a probability that component I has caused the system failure under the condition that the system is failed right at time t. So I guess you are a little confusing, but you'd better give 10 or 20 minutes to digest this concept. The important implication of this measure is we can prioritize the maintenance action. So if ICL, if a component I has the highest ICL, that means the component I has the highest probability that cause the failure of the total system. That means we should give our first maintenance action to the component I. So we can optimize the system reliability with these kind of tools. Returning to our original questions, which is the most important component in the system in terms of reliability. We introduced several importance measures to answer the question. So most important measure is bomb bomb, and you should remember another measure, criticality importance. There are another measure, fossil vessel. So you can read again the material. But then you should, let me give you another question. Then we can optimize the system design with the component measure, component importance measure. We have a system, okay? We have a system. Okay, our system has the reliability of HP. We know, after estimating the system reliability, we know that our system reliability is less than the target value. For example, our system reliability has 95%. Target value is 98%. So we need to improve our system's reliability. And there are many, many measures. Here we have bomb bomb, criticality importance. There are many, many measures. Then, can we optimize the system reliability? Or what I mean is, can we improve our system design to achieve the target value if we know the component reliability? That is my question. 한국말로 다시 얘기하면요, 우리가 시스템 reliability가 달성 못한다는 걸 알아요. component measure를 다 알아. We know the component measures, component importance measures, many in many forms. 여러 가지 형태가 있죠. Then can we optimize the system design? In a real world, the most important thing is the most important thing is money. Okay? We have just talked about reliability. We haven't discussed the effect of the component in terms of financial terms. So these kind of things are just the view from the reliability. There should be some consideration in a more modest term. I mean that we should think about the economics of the system change. What I mean is that in any way, assume that we came to know that component 3 is most effective in improving the total system reliability. But unfortunately, as always, component 3 is the most expensive component. Then do we have to stick to the component 3? That is the real problem we faced in the real world. So typically, we automatically think about the economics. Component 1 may be less effective than component 3, but component 1 is more cheap than component 3. Then we can add 3 we can achieve this improvement by adding 1 component 3. It's a little confusing, 1 and 3. Component A and component B. We need 1 component B to improve this 3% gap, or we can add 3 more component A to fill the gap between our target and the current reliability. Then we should think about the money, the economics of system design change. So what I like to emphasize is that these are just about reliability and mathematics. And the real world, you should think about the economics. So I think we'll cover the economics of the system. Let me talk about a little bit about the economics. So what kind of money do we have to consider? That's another question we should think about. One is the first money to purchase the equipment or install the equipment. That cost is called capital expenditure. Consider car. Capital expenditure is the money you should pay to the car selling company. But as you know, we need some money to loan our car. That money is called operating expenditure, like gas, fuel cost, or the maintenance cost for your car. So we usually call it KCAPEXP, CAPEX. CAPEX, this called OPEX. So the sum of these two costs is the real money we should pay. So what I mean is that you should not focus only on CAPEX. You should consider OPEX of the component. So when you think about the economics of component A and component B, you should consider CAPEX and OPEX together. In many times, as you know, OPEX is governed by the system reliability. What I mean is that your maintenance cost for your car will increase with the unreliability of your car. So sometimes the system reliability effect is separated from the OPEX, and these sometimes called diskex. risk expenditure. Risk X. This risk X can be the cost due to failure or accident due to the that are caused by the system unreliability. So we can say that the total cost is a function consists of three costs, three expenditure: capex, opex, and risk X. And another factor you should consider is that the time effect. Okay, so our car is not a kind of permanent machine. It has kind of life cycle. So this kind of activity or engineering to analyze the cost is called life cycle cost, LCC. So my emphasis is that optimization has meaning if and only if it is dealt with in terms of life cycle cost. Okay? Reliability is just a component of the optimization. So when you say optimal heat exchanger design, that doesn't mean that minimizing the heat transfer area or the minimizing the consumption of utility. Optimization of a heat exchanger should be minimizing the life cycle cost. Can you understand me? So the component measure is just aspect of reliability when we want to optimize the system design. Anyway, it is worth giving several minutes to digest the concept of the component measures. You don't have to calculate the component measure of a real system. Actually, it is really time consuming. Sometimes it is really impossible to manually estimate the component measure. So typical way is we construct kind of RBD, reliability block diagram, or fault tree analysis of a big system, and the commercial code can generate this kind of measures. So you don't have to calculate the component measure yourself. So important thing is you should understand the concept. Any questions? Now we will talk about dependent failures. 2 days ago, I promised that we will study the system reliability with dependent component. So this is the time for dependent component. There are 3 causes of dependent failures. First is common cause failure. Second is cascading failure. Third is negative dependence. So let's visit one by one. What is common cause? As the name implies, the failure that can be caused by a common cause, common design defect, material deficiency, installation error, maintenance error, harsh environment, support system. These kind of things are the causes of common cause failure. Common design fault, you can understand. Material deficiency, we have two pumpers. The impeller of two pumpers is manufactured by one manufacturer, and the manufacturer may use the same material for the impeller. So if the failure of the pump is caused by bad material for the impeller, we can assume that the second pump will fail sooner or later due to the common cause of bad material deficiency. Common installation error. There is a good practice to install some instrument, for example, but if they apply the same installation practice to all the components, and if it is turned out that there is some mistake in installing a component, we can guess that all the rest component should be subject to the same fault. Maintenance error, harsh environment. Environment can influence all the components to the same degree. So environment, what I mean is, I think returning to the definition of reliability, reliability is a function of environment. What is the definition of reliability? The probability that the system or component can fulfill its function for a given operating condition. So environment governs the operating condition. When we define the reliability of this electric bulb, the electric bulb should be installed indoor. If it is installed outdoor, the reliability cannot be guaranteed because the operating condition is changed. So reliability is function of environment, operating condition. So if we have harsh environment around our system, it is natural to assume that all the components may be subject to the similar environmental load, and they can be failed if one of them get failed. This is the common cause failure. Second, cascading failure is domino effect, chain reaction. Assume that we have two components, identical components. A common node is shared by the two components, component A and component B. For example, we have pump here. These two pumpers is supposed to deliver 100 kilogram per hour, and the load of each is just 50 kilogram per hour. One of them is failed, so the operator wants to send as much as water using component pump A. So the pump A is overworked. I mean, the flow rate is increased from 50 to 70. Then pump A should be subject to increased load. That means the environment operating condition is changed. So that we can guess that the component A will have higher failure rate at this increased flow rate. This is the type of cascading failure. That means, what is cascade? Multi-stage fall. Waterfall. You know waterfall? 폭포. So cascade is multi-stage waterfall. 다단폭포. So that means pump B failed. Then pump A is overworked. So pump A will soon get failed. So failure is cascaded. Negative dependence is the other side of the story. Now, pump B is failed, and the operator recognized the cascade failure mechanism. So, what they do is to stop the whole system and fix pump B. That means pump A is not operating, so the load to pump A is decreased. So due to the failure of the neighboring component, pump A's failure rate can be decreased. This type of failure mechanism called negative dependence. If we know the functional connection, the system configuration, causes 2 and 3 can be modeled. But we should do something about first type of failure. So that is the beta factor model. So beta factor model is for the common cause failure. These type 2 and type 3s are modeled using the change of system configuration. Okay, we can change the RBD or FTA, but the first type of failure, common cause failure, is hard to define. So we introduced the beta factor model. So I will explain the beta factor model in terms of mathematics, and we will discuss the limitation or the implication of this model. This beta factor model is the most widely used for common cause failure. The assumptions are there are n identical component. So identical component, the assumption of identical component is very important. We apply this model to 2 identical components, not like this. The component should be identical to each other, okay? Identical. So we can apply the beta factor model to a pump and to compressor. We can apply the beta factor model only to two identical pumps. Okay? Each component has two types of failure. Type 1 is independent failure. Type 2 is common cause failure. The fraction of type 2 is constant with respect to time. It's hard to understand in sentence, but it's hard to understand it is very easy to understand the concept in a graphical way. This is a total failure. There is a common cause failure. The fraction is beta. The rest, 1 minus beta, is the independent failure. Common cause failure, independent failure. This is type 1, this is type 2. So, this is the total failure rate. Failure rate of component I, not independent. Failure rate of common cause failure. Beta factor is the ratio of the common cause to the total failure rate. So the common cause failure and independent failure rate are expressed by these equations. You may remember this equation. On non-repairable parallel system, we have two parallel systems. Two independent components with the failure rate, lambda 1 and the lambda 2. This is, you can derive this equation, okay? And this is the MTTF. This is the failure rate function. We already learned this equation. In order to apply the beta factor model, the two components should be identical. So that means lambda 1 should be equal to lambda 2 because the two components are identical. So in order to apply the beta factor model, the component should be identical. So if lambda 1 and lambda 2 is equal to each other, the expression is simplified as these two equations, the total system reliability and MTTF. As the beta factor model, if you follow the beta factor model, component A, component B shares common cause failure whose fraction is beta. So for component A, 1 minus beta is independent failure rate. Beta is common cause failure rate. 1 minus beta B is the independent failure rate. So if you follow the mathematics, you can derive this equation. So you can see that you have a beta here. Two out of system. This is the reliability of system reliability two out of 3 system. And in this case, there are 3 components. Common cause failure has beta fraction. The common cause of component A and C, but not shared by component B, the fraction should be 0. Okay? There is no failure like this. if you follow the beta factor model. Okay? That should be clear to you. Okay, common cause failure is common to all the components, not part of component. So you can derive this equation. I guess you are very curious if the equation is correct or not. So it is homework for you to derive the equations. Okay, you can derive the two equations. So take a look at the textbook, and I'm sure you can derive the equation very easily. These four equations. I think it's the end of the course material. So think, guess why we deal with the common cause in real world. So there is a situation, we assume that we install, for example, pressure transmitter. Yeah, gas detector is a good example. In this room, we have assume that we have three gas detectors. Gas detector 1, gas detector 2, gas detector 3. These are installed on the ceiling, and they should be connected to a kind of control room. Okay? Assume that our OSE office is the control room. So there should be wiring line, electric line between the control room PLC computer to this line. So convenient way is that we have a line just here, and these lines are connected to each detectors. Then you can detect the gas. Okay? We have three detectors. Three detectors is connected to a line, and that line, this is kind of our door. When we have fire, then this line can be damaged. What I mean is that if we have a kind of disconnection in this line, all the three detectors cannot fulfill its function. It cannot detect the gas. These kind of things are common cause. So the correct way is that these detectors should be independently connected to the controller. This is the way we can avoid the common cause failure. That means we need more wiring or input-out connection in the control room. We usually call it cabinet, electric cabinet. Another example, common cause can be observed in any design. In many design, we can find a common cause. Assume that we have a LNG tank here. We wanted to measure the level of this tank. So we make a two nozzle here. Usually half-inch tubing, and install a level transmitter. But the owner doubts the reliability of this level transmitter. So they request that there should be another redundant level transmitter. So convenient way is we can have a T line here and install another transmitter here. Now you can understand. This two-level transmitter can be subject to a common cause failure here. Okay? If there is some material that blocks the tubing, even though the level transmitters itself are working very well, they are subject to a common cause. So this to avoid the common cause failure is very important when it comes to safety. Okay? In a BPCS, basic process control system, this kind of configuration can be acceptable. But the safety system is a kind of final barrier to the safety of operators and environment and to the society. So there are strict requirements about the common cause failure. Okay, sometimes it is called hardware redundancy. So anyway, the term is not important. The important thing is you should satisfy this kind of requirement when you deal with the safety system. So returning to the protection layer, do you remember the protection layer of safety system? The intrinsic safety, BPCS. This is the way of preventing the accident in a big system. The offshore installation, offshore plant has this kind of layered protection, and it's the same for the nuclear plant. Onshore plant are currently trying to implement this kind of protection layer. Anyway, there are inherent safety design, there are basic process control system, and we have safety system. And if we wanted to control the level, we may use some BPCS, like we can control the control valve, or we can control the speed of pump here. So BPCS try to control the level of this tank to 50%, and this pump should know the level of this tank. When this BPCS fails to control the level of this tank, there should be accident preventive protection layer. There should be level detection system, and the system should recognize the failure of the BPCS. So one way to implement the policy is that we have this. We install one level transmitter for BPCS, and we can use this level transmitter for the preventive protection layer. The level can be reported to the control room, and the control room safety PLC can issue an alarm. The level is increasing or the level is decreasing. But the requirement is that the level transmitter should not be shared by BPCS and the safety system. So it is quite sure that the BPCS can contribute the total system safety, but the safety engineers concerned the common cause failure. When BPCS cannot control this level, there is high possibility that the level transmitter is not working properly. Maybe the pump is not working correctly, or some valve is not working properly. But there is also probability that the level transmitter is not working correctly. So the requirement is that the level alarm system should have separate level transmitter. So that's why the plant instrumentation is complicated. If you are familiar with the ship systems do not have to satisfy the plant level safety. So in ship system, you usually have one level transmitter. That transmitter is used for BPCS and for preventive safety system. But in offshore practice, the instrumentation should be separated to avoid common cause failure. So we will soon learn about the reliability of safety system. There are several requirements. So you need to wait 2 or 3 weeks to learn that concept. Anyway, common cause failure can appear everywhere, every time. So you should pay attention to avoiding the common cause failure in designing your system. Any questions?